Aerospace advancements in World War I and World War II. World War I broke out on July 28, 1914, and was fought between the Allied powers and Central Powers all the way up until November 11, 1918. The first airplanes were used primarily for photo reconnaissance and gaining information past the constraints of trench warfare. Some of these first planes include the Fokker D-7, the BE-2 biplane, and the Sopwith 1 1/2 Strutter. The Strutter was a British-designed fighter and was first flown in 1915. It didn't take long in World War I for weapon advancements to develop among aircraft. Both sides immediately began installing and testing various weapons on board the aircraft. In 1915, the first machine gun was installed upon an airplane. The breakthrough invention was an interrupter device that gave the ability for a machine gun to shoot through rotating propeller blades without affecting flight. This new technology was first used on the German-designed Fokker Entdecker. Its advancement was a significant catalyst toward battles entirely in the air and ground support provided by air. After advancements in weaponry and maneuverability were invented, the war opened up to an entirely new form of warfare. Now entire battles were fought solely in the air between planes. This created a new kind of military role as well. Governments on both sides made sure to spread propaganda about airman successes in order to gain more civilian support. It also evolved war strategy. Much of these air battles were crowded and extremely dangerous dogfights. This is how large formations of planes, patrols, and air aces emerged. First awarded by France, any airmen that downed at least 5 aircraft were designated as air aces. You may know of the Red Baron. He was an air ace with the highest score by the end of the war with 80 kills. 21 years later, World War II began. It was fought between the Axis powers and the Allies, starting on September 1st, 1939, and ending September 2nd, 1945. At this point, plane and engine design were better than ever. Traditional materials like wood, plastic, and cloth were replaced with sleek and sturdy metal, mainly aluminum. Piston engines were able to provide the amount of power needed to increase speed, max altitude, and maneuverability. Jet engines were tested and installed in World War II, but due to inefficient fuel usage and poor aircraft design, they did not reach their full potential and were not often used. Some of the superior air machines were Mitsubishi's A6M fighter plane, the P-51 Mustang, and long-range bombers like the B-17 and the B-29. The P-51 was one of the most significant aircraft in the war. It had the speed and range to escort long-range bombers to their drop targets. Along with these advancements, planes started to be designed as more multi-use. For example, the Lockheed P-38 Lightning Fighter Interceptor was capable of bombing, as well as accurate photo reconnaissance. There were many key technological advancements that allowed military planes to operate more effectively and to extreme levels. Pressurized cabins were very important in the war, and for commercial use after the war. These cabins were introduced to long-range bombers like the B-29, so that they could operate from a very high altitude without bulky body equipment. Another technological advancement brought to bombers was the bomb sight. This was a targeting sight that was used to drop bombs on precise areas from high altitudes. The scope considers the plane's speed, altitude, wind speed, and flight path when calculating the precise time to drop the payload. The bomb sight made tactical bombing, according to photo reconnaissance, very threatening towards high-profile enemy targets. Finally, radar was developed throughout the war. It had both offensive and defensive uses. On aircraft, its use was primarily offensive. Pilots could use radar to target enemy planes during the night and fire upon their location. On the other hand, pilots could be alerted of approaching enemies and evade before they were attacked. Advanced projectiles that could be guided without a pilot were very destructive in the war. Created towards the end of the war, Germany developed V-2 missiles that were used to rain large attacks on enemy bases and towns. These were among the first long-range missiles. The first missiles were guided using radio waves to pilot their course. Eventually, the U.S. took it a step further and designed a missile that could be completely self-guided by utilizing radar technology. Weapons like these were able to be stored out of sight and then unleashed on the enemy with a massive impact in a short amount of time. The Fritz X was a prestigious German-designed guided bomb. Its main purpose was to pose a threat against enemy ships. It had qualities that could break through and destroy entire Navy ships.
My name is Christopher Kirshner, and today I'm going to be talking about military aerospace innovations. Here are the U.S. military's top 3 aircraft used. The first one is the F-22 Raptor, number 1 in air-to-air combat. The F-22 Raptor was specifically designed for extreme maneuverability and stealth, capable of Mach 1.95, reaching a speed of 1,500 miles per hour. And as it's so fast, it's invisible to most radars as they can't detect the plane. The F-35 Lightning is a more compact version of the F-22 with ground capabilities as well, reaching Mach 1.07 with a single engine and vertical takeoff and landing. The F-18 Super Hornet is flown mainly from aircraft carriers and can reach Mach 1.8, which is 1,380 miles per hour, with superior air-to-ground surface capabilities. The F-35 was designed and built by Lockheed Martin in 2006 and has been sold to 13 different countries so far. Weapons capacity for the F-35 includes 18,000 pounds of ordnance. For the stealth-wise, they have very low observation and can evade enemy detection and enter contested airspace. For sensor fusion, the aircraft can create an integrated picture of the battlefield to enhance awareness and survivability. The F-35 Lightning is also unique in that it has 3 different variants: the F-35A, B, and C. The F-35A is deployed by the U.S. Air Force with conventional runway takeoff and landing, and the F-35A carries the most ordnance out of the 3. The F-35B is deployed by the U.S. Marines, highly deployable in very adverse landing situations, and you can see the lift fan and how the short takeoff and vertical landing works. These are also smaller and more compact than the other 2 versions. The F-35C is deployed by the U.S. Navy and is specifically built for aircraft carrier operations with the tailhook and extended wing length. So the F-35 Lightning actually gets kind of a bad rap in the media coverage in general because a lot of media sources focus on its downsides. However, the national interest actually talks very favorably about the F-35 and all of its capabilities. It also demonstrates, Mrs. Lauren Thompson talks about how the F-35 was very needed in the current environment it is now. World events happening around the time of the F-35 being designed and tested are the War on Terror and also now the race for arms between the global powers, China and Russia. The F-35 made huge leaps in the aerospace community with one-engine air thrusters and the fact that the engine can rotate 95 degrees in 2.5 seconds, basically taking the capabilities of the Osprey, the MV-22, and putting them into conventional jet. The F-35 was a huge leap in aerospace community, and especially came out on top for the fifth generation fighter jets in general. The F-35 has also set the pace for rapid production of aerospace dominance.
The Cold War Space Race: Advancements and Achievements. Presentation by Riley Greenberg. In the second half of the 20th century, tensions between the USA and the USSR were at an all-time high. This is because of their disagreements on different political and economic systems. This tension and disagreement manifested in several ways, one of which was the space race. They competed to create new space travel technologies before the other, and to reach the moon first. Some important events during the space race include Sputnik 1, the first satellite, Laika the dog being sent to space as the first animal in space, Yuri Gagarin as the first human in space, riding on Vostok 1, Alexei Leonov performing the first spacewalk, Zond 5 being the first spacecraft to orbit the moon and return, Apollo 8 becoming the first crewed flight to orbit the moon, and the first humans landing on the moon in the Apollo 11 mission on July 20th, 1969. The Apollo 11 moon landing could easily be said to be one of the most important human achievements. It was the first time humans ever touched another planet or moon. This is so significant because it paved the way for all of our current space exploration of other planets like Mars and other planets in the future. The technologies that were created that made the Apollo 11 moon landing possible paved the way for current technologies that are still used today. It was really a turning point in human history, especially space exploration. The events of the Apollo 11 mission occurred as follows. Apollo 11 launched from Kennedy Space Center, now called Cape Canaveral in Florida, on July 16th at 9:32 a.m. Then, on July 20th at 4:17 p.m., Apollo 11 arrived at the moon and touched down that same time. Astronaut Michael Collins stayed on the Columbia spacecraft in orbit of the moon, as Neil Armstrong and Buzz Aldrin touched down in the Eagle lander. They spent 21 hours on the surface, collecting samples and data about the surface of the moon, and leaving their mark on history. On July 24th, Apollo 11 splashed down in the Pacific Ocean near Hawaii.
At 15 seconds, guidance is internal. 12, 11, 10, 9. Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. We have a liftoff. Liftoff on Apollo 11. Shadow. 4 forward, drift into the right a little. 30 seconds. Forward, drift. Contact light. Okay, engine stop.
Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're going to be busy for a minute.
Armstrong is on the moon. Neil Armstrong, 38-year-old American, standing on the surface of the moon. On this July 20th, 1969.
It's one small step for man, one giant leap for mankind.
Oh, that looks beautiful, Neil.
It has a stark beauty all its own. It's like much of the high desert of United States. It's different, but it's very pretty out here.
Beautiful view.
Isn't that something? Magnificent sight out here.
Magnificent desolation.
Tranquility Base, use of guidance recommendation is pings
on the runway. 7, 6, 5, engine arm ascent. Beautiful. Very smooth. Very quiet ride. Apollo 11, this is Hornet, over. Apollo 1, this is Apollo 11, reading you loud and clear. Our position 1330.
The Apollo 11 crew consisted of Neil Armstrong, Buzz Aldrin, and Michael Collins. However, they were not the only people that made the mission possible. Hundreds of NASA scientists and engineers also had a part in the mission. They worked on developing the technologies that allowed the mission to be possible, as well as facilitating mission control from the ground and making sure that everything went well. Many technologies contributed to the success of the Apollo 11 mission. These include the Saturn V rocket, the rocket that the mission used to lift off from Earth. In addition, the Extravehicular Mobility Unit spacesuit, which Neil Armstrong and Buzz Aldrin used to walk around on the moon safely. In addition, the Columbia spacecraft, which orbited around the moon while they had landed on its surface. In addition, the Eagle lander, which allowed them to land onto the moon in the first place. And rocket propulsion as a whole, which without this, they wouldn't have been able to even leave the Earth's orbit. Also, the scientific instruments the astronauts used on the moon to collect samples and data were vital to the mission's success. The technologies of the Apollo 11 mission, as well as the technologies of the space race as a whole, have had a massive lasting impact on today's scientific climate. If it hadn't been for most of these innovations, such as the first human in space and the first satellite, we would never be able to one day have the first humans on Mars, and even other planets beyond that. The technologies created in the Cold War space race have also influenced today's current rocket technologies, like NASA's Space Launch System and SpaceX's rockets. Overall, the impacts of the space race will never be forgotten in the industry of aerospace and space exploration.
History of unmanned space exploration. The very first unmanned space probe was Sputnik 1, which was also Soviet-made. Sputnik 1 was the first space probe to orbit Earth and send signals back to the ground. And when the US heard of this, they became worried about the technological gap between them and the USSR. So the space race eventually began, and NASA was founded a year later. Luna 1, which was also another Soviet space mission, was dedicated to exploring the moon. Luna 1 was the first spacecraft to orbit the sun, but however, the goal, which was to impact the moon, was not achieved. Luna 3 eventually did orbit the moon, and Luna 9 was the first space probe to actually land on the moon intact. Lunokhod 1 was the first robot to land on the moon. Later on, the US would make Surveyor 1, which would be the first probe to actually take samples of lunar rock for study. Mariner 9, US, becomes the first probe to orbit Mars, while Viking 1 and 2 were the first probes to actually touch down on Mars and send data back to Earth. And at this point, the US has caught up in the space race. In 1973, humanity makes its first attempt to communicate to possible extraterrestrial life. The US-made Pioneer 10 was launched at the deepest depths of space, and also while carrying a golden plaque which contained info about humanity. Some things were such as a depiction of a human male and female, our solar system, our planets, as well as which planet we were from, and also other signs of human intelligence. Voyager 1 inevitably left the solar system in 1983. 4 years later, the U.S. launched the Voyager mission. The purpose of this mission was to explore the outer solar system. Voyager 1 was launched the same year and was the first probe to actually send back pictures of Jupiter and was also the first probe to go past Uranus. Voyager 2 did around the same thing, which was just studying the outer solar system. After the space race had concluded, humanity started looking towards its neighbor Mars. The US-made Pathfinder became the first of multiple Mars rovers to explore the surface. Later on in 2012, Curiosity, which was also US-made, studies Mars for geology, weather, and signs of pre-existing life. Other modern events in which play a significant role in unmanned space exploration include the current Cassini mission, which is studying Saturn's moon Enceladus for signs of life, as well as Elon Musk's first successful launch and landing for reusable rockets.
So I'm doing the research on supersonic flight, and the date of the achievement was October 14th, 1947, by an Air Force pilot who was Major Charles E. Yeager. And he reached up to 700 miles an hour, which is Mach 0.1, at an altitude of 43,000 feet. Dr. D. Beeler was an aeronautical engineer for NACA and basically helped the design of the X-1, which was the engine which was the plane that achieved this goal. Slick Goodland was the test pilot for the X-1. Chuck Yeager was the captain of the United States Air Force and was assigned to be a test pilot in the air for the X-1 program. And James Hartwell designed, built, and tested the rocket with the help of D. Beeler, Slick Goodland, and Chuck Yeager. So these are some pictures of the X-1 rocket. It's shaped like a bullet, and it's very small and compact with the big rocket engine and with fuel and not enough space, or not a lot of space for the pilot himself. So this is the description of the plane and the engine, I guess. And so it was originally called the XS-1, and it used direct nitrogen pressurization for the fuel system instead of using turbo systems. And the plane was really small, with a wingspan of 28 feet and a length of 31 feet. And it had a pressurized cabin, retractable landing gear, and 2 propellant tanks for the gas. So it was very compact and small, I guess. And it had 6,000 pound thrust, or it had a 6,000 pound thrust rocket engine and more than 500 pounds of special flight test instrument. So these are some quotes from from Yeager and Goodland, and they basically say, or Goodland basically says just how big it was, and or how small it was, I guess, and how compact it really was. And then Yeager said that basically once you drop out of the B-29, which was the ship that was, or the plane that was carrying it up to 40,000 feet, and he said once you drop down from it, you cannot control the throttle. You just go, and you just run it until it runs out of fuel. So these are more supersonic flights, and so the Tupolev Tu-144 was the first supersonic transport made by the Soviets in 1969, and began delivering mail in 1975 and started carrying passengers from 1975 to 1999. So this Lockheed's SR-71 Blackbird was the first plane, or the world's first stealth supersonic plane that was non-rocket powered and had a cruising speed of Mach 3.2 and had and was capable of producing a static thrust of 32,500 pounds per foot, I think. And then the Concorde was the first supersonic commercial plane that's made it, and it made its first transatlantic crossing on September 26, 1973, from France to Great Britain. So this is the future of supersonic flight, and so United Airlines bought 15 planes that could travel at Mach, or that could cruise at Mach 1.7 or 1,300 miles an hour, which means it could potentially cut the time from Newark, Delaware to London from 7 hours and 50 minutes to 3 hours and 30 minutes. And they plan to schedule trial flights in 2026, but might make it an official, or might take an official flight in 2029. But the problem with this is that the gas could be expensive, but they said they pledged to reach zero emissions by 2050 and would be the first plane to ever use 100% sustainable aviation fuel. And this is basically like what you get on the pictures is what you get about when you fly with Concorde, I guess. But yeah, that's it. Thanks for listening.
This presentation is about rotorcraft. So rotorcraft are a form of aircraft that have several rotors that spin around a central point. And the rotors are basically shaped like the regular types of wings you'll find on an airplane, except they're long and stretched out. They have like an airfoil on them, and when it moves through the air, what that does is it generates lift, so it'll want to lift up. On a regular airplane, the wings are fixed, so the lift is generated as the airplane moves forward. But with rotorcraft, since the rotors are spinning around, the air is flowing over them while the rest of the aircraft is staying stationary, which allows them to hover in place, like you can see this helicopter doing in the picture. And this was a really big advancement in aerospace technology because before you had planes and that needed to be moving in order to generate lift, which means you have to have a long runway in order to take off or land. But with helicopters and rotorcraft, all you need is a short area for them to be able to take off of and land. The first practical and successful helicopter was the Vought-Sikorsky VS-300, which flew on May 13th, 1940 for the first time. And this was the first time that it flew untethered, because they had done previous test flights where they had it tethered so it wouldn't fly away and crash and all that. But this was the first time it had flown untethered. And what's interesting about this helicopter is it was really the first practical one. There had been previous kind of concepts and designs, but none were nearly as successful as this, because they were able to go up, come back down. They weren't really able to maneuver much, which is why the VS-300 was the first practical helicopter in the U.S. And in the world. So it was flown first in Stratford, Connecticut, and it was designed and flown by the Russian-American inventor Igor Sikorsky. After seeing the helicopter fly for the first time, it began to draw a lot of attention from the public. You can see the newspaper article attached, and a lot of news sources were writing about this new breakthrough in aerospace technology. But another thing that happened was at the time that they made this advancement, it wasn't quite to the point that the U.S. had entered World War II, but shortly after they would when the Japanese bombed Pearl Harbor. But they began to see a lot of possible military applications for the helicopter. And later on in World War II, towards the end of the war, they started using them from some designs that were based off of the VS-300. And as I'm sure many know, these days there are plenty of helicopters in our military, so they were very important. And you can also see there's a video attached of one of the flights of the VS-300. The invention of the helicopter was made possible by many previous inventions. The biggest one, of course, was the Wright brothers' first powered flight in 1903, which really served as proof that something like this would be possible, because the plane was generating the lift from the forward motion with the air moving over it, but it was getting that forward motion from the engines that were powering it, and it wasn't just a simple glider that used gravity to create the lift as it went down and gained speed. And they just kind of went off of that. So you have the wing that generates the lift. The idea was you take this wing, the concept that's already been proven through previous flights, and you spin it around really fast, and you can generate lift. And obviously with the design of the helicopter, the body of the aircraft doesn't need to be moving. It can stay stationary. Sikorsky's helicopter had a major impact on future aerospace developments. There have been plenty of different innovations off of his design, and that's what we have for many modern-day helicopters. There are helicopters used in the military, used for search and rescue, for personal and recreational use, and they all use different types of designs. There are big helicopters and small helicopters, so it's a very versatile machine that's been used for many different applications that's improved many lives.
Hello, my name is Grady McConnell, and one of the most important or outstanding achievements in aviation is the development of the V-22 tilt-rotor Osprey. The V-22 Osprey, produced by Boeing and Bell, is a revolutionary new kind of aircraft developed in the mid-1990s to address the issue of close-quarter takeoff while having the range of a fixed propeller aircraft, or of a fixed-wing aircraft. So, to solve the issue, Boeing and Bell developed the V-22. The V-22 is a tilt-rotor military aircraft with a unique hybrid design that combines features of a helicopter and a turboprop plane, allowing it to take off and land vertically to minimize on space for takeoff, but once airborne, to be able to rotate 90 degrees from an overhead to front-facing position to allow for higher speeds, further distance, and a higher weight capacity. The signature feature of the V-22 Osprey are its tilt-rotor engines. To power each of these propellers, the V-22 utilizes two Rolls-Royce-produced T406 turboshaft engines. Each of these delivers enough force to be able to rotate each of the propellers to allow for vertical takeoff, as well as, once in the air at a cruising altitude, to be rotated 90 degrees forward to turn the helicopter-like aircraft into a propeller aircraft with fixed wings, allowing for greater speeds, distance, and maneuverability. In addition to its ability to have a vertical takeoff while transitioning to a propeller aircraft while in flight, the V-22 Osprey has incredible weight capacity. Its max liftoff weight, when ascending vertically, is 47,500 pounds, but on short takeoff, it can lift up to 55,000 pounds, enough to carry light vehicles or, as seen in the picture, heavy loads of materials. Because of the complexity of the V-22 Osprey, at least 3, but no more than 4 crew members are needed at all times on the aircraft: the pilot, the co-pilot, and 1 to 2 flight engineers to ensure a smooth flight with little to no issues. The V-22's large capacity for weight, its large cargo area, and its ability to take off vertically makes it a key choice for most special operations or marine deployment. And that is because, unlike most helicopters, the V-22 Osprey can fit 24 combat troops in addition to its 3 to 4 crew members. The typical helicopter can hold up to max around 20 people. So with addition to having 4 more people on board, it can also carry all their equipment for rapid deployment and pickup. Being able to take off and land vertically comes with its benefits, not just for maximizing on space, but also to be able to access hard-to-reach regions, which is key in special operations deployments, but also just in providing resources and help for areas in need. This allows the V-22 to fit into places where no other aircraft could, or if a helicopter could, to be able to provide that extra weight capacity to be able to provide more help in a shorter amount of time. Another key and special feature about the V-22 Osprey is its built-in resistance to chemical, biological, and radiation attacks, making it so that if a special operations group was being deployed and was attacked by a chemical agent, it would be fully protected. The V-22 is currently being used by primarily the United States Marines, but also by the United States Navy, specializing in search and rescue, and the United States Air Force to specialize in its deployment of special operations groups. Despite its advantages of higher weight capacity, higher troop capacity, its ability to fly 250 knots per hour at max weight and fly over 200 nautical miles at max weight, its carrying of more fuel, a 50 caliber nose gun, and more advanced avionics, the V-22 is more susceptible to a vortex ring state than other military aircraft. That being said, the V-22 is the choice aircraft of the United States Marine Corps and is being used more often now than ever, especially since issues are being resolved every day.
Well, hello everyone. My name is Fletcher Port, and today I'm going to be talking to you guys about propulsion. So we really have 3 different parts to talk about here. So, the first one that we're going to break down is airplane propulsion. So we're going to start off today by talking about 4-stroke engines, get a good idea of, our basic, most efficient propulsion method at this time, and then we're going to kind of move into propulsion in the atmosphere. So, how do we kind of get out of here? How do we move around in our atmosphere vertically? And then, once we're out of our atmosphere, once we're in space and we don't have access to oxygen anymore, how do we move around in that instance? So those are really going to be the 3 main things that we focus on. That'll give us a really good understanding of propulsion all around. And I think that that's going to really be some of the key things we're going to need to know as we look at propulsion. So let's dive right on into the 4-stroke engine. It's the way that a lot of our cars operate. It's the way that a lot of our airplanes operate. It's the way a lot of things motor-wise operate. So basically how these work is you have a venturi that will mix, it's also called a carburetor, and depending on, airplane or car, things like that, but they will mix your fuel and your air together, and then it will come on into its first stage. So it'll come into the chamber by the piston coming down and the fuel coming in. You can see the blue and red are representative of the fuel and oxygen. And then the piston will rise and it will go upwards and it'll compress up that fuel and oxygen mixture. And then if you think about it, you have fuel, oxygen, and now you just need an ignition source. Well, then you're going to have an ignition come from a spark up at the top. That's your spark plug. And that'll send that piston back down. And when it goes down, that's going to be a big fast force that rotates the axle that it's on. That axle typically connects to a propeller or something like that. Maybe it's, the tires on your car, things like that. It'll then go down and the exhaust will get all of that gas out of there and the cycle will repeat. That's what you see in your cars when it says RPMs. It's how many times those pistons are rotating per minute. And keeping that in mind, let's go ahead and take a look at airplane propulsion now. So we think about our airplanes and yeah, I mean, kind of ideally the same thing with cars in terms of the four-stroke engine. That four-stroke engine operates, it's spinning that axle, and that axle goes to the propeller. That propeller then has an angle on it, and that angle, as it cuts through the air, is pushing air backwards, and it's pulling whatever that axle or that propeller is connected to forwards. I mean, commonly forwards, right? Sometimes you might have a propeller that faces in the opposite way, but that's another story for another time. So that propeller is rotating and it's bringing the aircraft forward. Then we have the turbine, and that really is the same way in that it has all these different propellers. You can see a turbine example right there. It's not just two propellers. It's not just two fans attached onto the prop. It's a number of them, a large number of them. And when that happens, it's because you're really going to generate a big amount of thrust when you do that. The nice thing about turbines is they actually can adjust while in flight. So, when you're on the ground and you've got a certain density of air, you might want it to be a different angle than you have it when you're up in higher altitudes and you've got less dense air. So that really helps for the efficiency of a turbine. You've got ramjets, which those aren't used too commonly, but a little fun fact about them, they actually changed their name to a scramjet after Mach 5. And last but not least, we have the rocket. That's the one that we're really going to go into today, is how do rockets work? How do they make propulsion for spacecraft? So if a rocket wants to go somewhere, if it wants to make propulsion, we need a fuel. And the fuel that a lot of rockets actually use is called liquid hydrogen. This is actually an older method. It dates back to 1965. The Apollo missions actually averaged 600,000 gallons worth of liquid hydrogen per mission. It's been commonly used over the decades. And what's nice about it is you simply mix liquid oxygen and hydrogen, and then you burn it at over 3,000 degrees. When you do that, you make a lot of energy, you make a lot of propulsion, and that's what a lot of spacecraft use to get out of our atmosphere and to get out of Earth's pull. And so once we've hit that escape velocity and we've gotten out of our atmosphere, we need to move around in a vacuum, right? We don't have any air. And so while using liquid nitrogen to propel us when there's no air and therefore no drag would be awesome, you can't use liquid nitrogen or liquid hydrogen, because if you burn liquid hydrogen, you don't have any oxygen to do that. So instead we use a hydrazine monopropellant, and that works by basically heating up a gas, being hydrazine, and then shooting it out of this little chute at the bottom that you can see in this image. And when you do that, it moves like the bow thrusters on a boat. By just, you push water out of your boat, you're going to move in the opposite direction. You push this hydrazine out of that chute, you're going to move in the opposite direction. That's the way to do it. So you're just heating up a gas and letting it kind of explode out of this little chute to get you moving. And that's really helpful for when you're in space and you need to make minor adjustments and things like that. So hopefully this helped you guys kind of understand better propulsion and how we do it, both on ground level and in the atmosphere and even out of the atmosphere. Thanks guys for listening. And so once we've hit that escape velocity and we've gotten out of our atmosphere, we need to move around in a vacuum, right? We don't have any air. And so while using liquid nitrogen to propel us when there's no air and therefore no drag would be awesome, you can't use liquid nitrogen or liquid hydrogen, because if you burn liquid hydrogen, you don't have any oxygen to do that. So instead we use a hydrazine monopropellant, and that works by basically heating up a gas, being hydrazine, and then shooting it out of this little chute at the bottom that you can see in this image. And when you do that, it moves like the bow thrusters on a boat. By just, you push water out of your boat, you're going to move in the opposite direction. You push this hydrazine out of that chute, you're going to move in the opposite direction. That's the way to do it. So you're just heating up a gas and letting it kind of explode out of this little chute to get you moving. And that's really helpful for when you're in space and you need to make minor adjustments and things like that. So hopefully this helped you guys kind of understand better propulsion and how we do it, both on ground level and in the atmosphere and even out of the atmosphere. Thanks guys for listening.
Mid-air refueling. Mid-air refueling, which is also known as air-to-air refueling, is a method of refueling an aircraft without needing it to land. This is frequently used in the military to allow for planes to stay in the air for extended periods of time. The first flight across the U.S. was made from New York to San Diego by Lieutenants Oakley Kelly and John McCready in 1923. This flight lasted 26 hours and 50 minutes. The first air-to-air refueling was completed by Lieutenants Lowell Smith and John Richter on June 27, 1923. They later set the world record for the longest flight using air-to-air refueling. Two methods are used to refuel a plane in midair. They are probe and drogue and flying boom. Both methods require two aircraft, one tanker with fuel, and the aircraft that is getting refueled to approach each other mid-flight and fly within 100 feet of each other. The probe and drogue method uses a long hose-like connector to connect the aircraft. Once a secure connection is made, refueling begins. The flying boom uses a telescoping tube to connect the two aircraft. An operator in the fuel tanker lines the tube up to the other plane and connects them. This method is faster than probe and drogue, refueling at 6,000 pounds of fuel per second compared to the probe and drogue's 2,000 pounds per second. During refueling, planes must fly at the same speed. If one plane speeds up or slows down too much, the planes will disconnect and the process will start over. Refueling a plane midair can take around 15 minutes. Mid-air refueling is mainly used by the military. It is used to complete various missions, some of which may require refueling multiple times. The use of mid-air refueling became much more common after World War II and the U.S. getting involved in the Cold War. The advancement of mid-air refueling has led to longer flights and has extended some bombers' range by nearly 1,500 miles. Some advancements in aerospace engineering that make mid-air refueling possible and useful were the first powered flight, tanker planes, and the development of military aircraft.
This presentation is about flight systems, and flight systems are the systems in planes and helicopters that help the pilots fly safely. The first system is pitot tubes, and they were originally invented to measure water flow in like rivers and stuff by Henry Pitot, and they're named after him. But now they're used in airplanes and helicopters to find airspeed, altitude, and vertical speed, which is how fast you're going up or down. And they work by using two holes on the pitot tube. There's one in the front on the tip, and then a few on the side. And the one in the front measures the pressure of the air that's moving over the pitot tube, and then the ones on the side measure static pressure, which is pressure without anything coming at it, which you can see on the diagram. And by measuring the difference of the two pressures from the two different ports, you can find the airspeed. And with the static pressure, you can also find altitude, which is how high you are, and vertical speed. And most pitot tubes now have heaters in them to prevent ice from building up on them, which can mess with the reading, which would tell the pilot wrong information, which could be dangerous. The next system is radios, and they were first used on aircraft in 1916, and today they're mainly used for communication and navigation. And that's very important because without being able to communicate with other airplanes and people on the ground, you could run into somebody, and that'd be very bad because people would die. And they're also very useful for finding where you're supposed to be going. They can also be used in radar systems, which kind of goes with safety because it helps people on the ground tell airplanes how to stay far apart. And GPS goes with navigation because GPS satellites use radios to find where you are. And they're also used by other systems to find other airplanes around you, so you know where they are and you don't have to worry about hitting them. They're very, very important for safety because they can help pilots stay far apart and get where they're going. This is an example of radios in a plane. On the bottom right, on the top, the one with the screen is a radio, and so is the one below it. Most planes have multiple radios. Some of them are used for navigation, some of them are used for talking to other planes, and some of them are used for getting weather. So you need to have a few of them, and this also provides redundancy, so if one breaks, you have others to fall back on. The last systems are GPS and ADS-B, and I have them on the same slide because they kind of go together and they help each other. GPS was first used in aviation in 1994, and it plays a big role in modern aviation because it's very useful for finding where you are and backing up the traditional ways of navigation with radios and just looking at landmarks on the ground. It's much more reliable. It feeds data to ADS-B, which is a system that helps the pilot find other planes around. So if you look in the bottom right at the picture, it's an example of a ADS-B display. So every one of those arrows is a plane, and it has its call sign, its altitude related to you with the plus 12 or minus 8 or whatever. So it would be like 1,200 feet or minus 800 feet, and also the direction that they're going. So that's where the arrow is pointing. So that's all very useful for finding where they are and where they're going so that you can avoid them effectively. And that works by having GPS data sent to other planes along with altitude and direction. And then the other planes use their radios to listen to that and display it on one of these displays. ADS-B stands for Automatic Dependent Surveillance, and it's very useful in modern aviation. These are my citations.
The first major step to going over the evolution of drones would be to define what a drone is. A drone typically is any aerial vehicle that is guided remotely, autonomously, or it could even be both. They often can carry sensors, and in military situations, they might carry target designators, offensive weapons, or electronic transmitters that interfere or destroy enemy targets. They are descended from target drones and remotely piloted vehicles used after World War II. The UAV is a broader term that could refer to drones, like electric vehicles that could fly, whether it's radio signals or something else. While something like A UAV could be something like a hot air balloon. They're most interchangeable, but UAV is a bit more broad. During the late Vietnam War, reconnaissance drones were first deployed on a large scale by the United States. They were used as decoys in combat, launched missiles at fixed targets, and they dropped leaflets on populations for psychological warfare. In 1973, Israel developed UAVs for surveillance and scouting. They were called the Massif and IAA Scout series. These were two major times when drones were developed by foreign countries, and they were used in a major military conflict. After the Vietnam War, countries outside the US and Britain started exploring unmanned aerial technology. New drone models were created that had improved endurance, could reach higher heights, and some even used solar power to make longer flights. Some of the major drones developed were the RQ-2 Pioneer drones, which was developed between the US and Israel. They were upgraded IAA Scout drones with a higher payload. They were used during the Gulf War. This was also the first time drones were used 24/7 during the Gulf War for military surveillance and targeted attacks. This was a major period of development for drones, with the U.S. leading the pack. The Predator drone is one of the most important drones in modern history. It was developed in 1996 and first deployed. It's the first ever drone platform to be used in major military weaponized situations for military strikes and attacks. It's a drone people think of when they hear about terrorists being attacked. The Predator drone was powered by a piston engine. It could go about 80 miles an hour, and it had an endurance of about 24 hours. It carries things like visible and infrared television, synthetic aperture radar, and many other tools like anti-tank missiles or other missiles that could be used for targeted strikes. Control inputs and sensor outputs were transmitted via communication satellite, and this has been a major drone used in military conflicts by the U.S., and has even led to some allies buying them and pushing other countries to develop them for these conflicts. The MQ-9 Reaper has improved performance. It is the modern drone developed from this platform that is used today by the United States.
Rocket fuel research. Jack Miller. There are two types of rocket fuels, just solids and liquids. Solid rocket fuels are much simpler and more reliable, although they burn out sooner and won't stop till their fuel is finished burning. Along with this, there is no way to control the thrust. The solids include ammonium nitrate, ammonium dinitrate, ammonium perchlorate, and potassium nitrate. Liquid rockets use a fuel and an oxidizer as their propulsion. The liquid fuels make it easier to control thrust because the liquids can be added as the flight takes place. This is the reason it is used in astronautical rockets we have today. The liquid oxidizers include nitric acid, liquid oxygen, liquid fluorine, and nitrogen tetroxide. In the fuels category, there is kerosene, alcohol, hydrazine, liquid hydrogen, and supercooled methane. In the early 1900s, Konstantin E. Tsiolkovsky theorized deep space travel with liquid rocket fuels. On March 16, 1962, Robert Goddard finished creating a 10-foot tall rocket which used liquid oxygen and gasoline as the propellants. In Worcester, Massachusetts, He launched this rocket 41 feet into the air in 2.5 seconds, with an average speed of 60 miles per hour. His wife and 2 co-workers were there to witness it. A few months later, he wrote a paper called A Method of Reaching Extreme Altitudes in the Smithsonian's Miscellaneous Collection. He originally did not want to write this piece. He was forced to write it by Charles Greenlee, who was one of the Smithsonian's lead writers. Charles used the funding which the Smithsonian offered him as leverage. The rocket could not have been built without the Smithsonian's money, so Greenlee forced a paper out of him. With the extra funding the Smithsonian gave him, he was able to put a camera and a barometer on it to start constructing new technology on the rockets. This was a huge accomplishment at the time, because many looked at him as a fool and anyone who theorized these ideas. After the paper came out, he was a big hit and started receiving more funding from people not only the Smithsonian, but from all around the world, including Germany. Some major world events in 1962 were the U.S. Great Miami Hurricane, one of the largest hurricanes to ever hit American soil, the UK coal strike, where miners would try to get money out of the government by going on strike. In the UK, John Beard shows the first TV in public. The Germany and the USSR signed the Treaty of Berlin. Hirohito becomes Japan's new emperor. In the US, Henry Ford makes cars available to the masses and cheap enough. Along with this, the first SAT test is given. And finally, Harry Houdini dies. Some engineering advancements is the ballpoint pen, the first run-through with turboprop engine, an instant camera. Ronald Odson flies over the North Pole with Nordship and his crew. Wasaburo Oshii first describes a jet stream in a published paper. Einstein's first refrigerator, displayed above in the picture. Wolfgang Pauli also discovers the observed spectrum of the hydrogen atom using Heisenberg's matrix theory of quantum mechanics. And finally, the past and the future. In the past, 13th century gunpowder was created in China, Chinese. They created guns and fireworks. The guns were then spread west and now are in almost every country in the world. In the 1300s, steam power was experimented by with scientists. They attempted using steam-based or water-based steam for powered flight. This never really took off figuratively and literally. Gunpowder-based weapons like the fireworks were soon developed into missiles fueled by liquids for war, World War II. Going to the future, the oxygen liquid iodizer and gasoline Goddard used is expanding upon using other fuels. At NASA right now, the main liquid is hydrogen fuel and oxygen iodizer, while NASA's JPL, Jet Propulsion Laboratory, is dedicated to its research in Pasadena, California. Along with this, SpaceX is researching other types of fuel, like the supercooled methane explained earlier. This can only be used in things like the Raptor engine due to the temperature regulations. There are many other fuels out there and coming up that may need similar accommodations. Thank you for watching and listening.
Current events in rocketry and SpaceX's Starlink. The billionaire SpaceX CEO is launching satellites into orbit and promising to deliver high-speed broadband internet to as many people as possible. After years of development within SpaceX, and after securing nearly $885 million in grant funds from the Federal Communications at the end of 2020, Starlink's progress seems to be accelerating in 2021. In years since, SpaceX has deployed over 1,000 Starlink satellites into orbit across dozens of successful launches. In May 2019, SpaceX launched its first 60 satellites into orbit. There are currently over 1,600 Starlink satellites in orbit, and that number will continue to grow over the following months as SpaceX plans to file paperwork for up to 42,000 satellites. Just like existing providers of satellite internet like HughesNet or Viasat, Starlink wants to sell internet access, particularly to people in rural areas and other parts of the world who don't already have access to high-speed broadband. All users have to do is set up a small satellite dish at their home to receive the signal and pass the bandwidth to their router. Although, in addition to fears that we're adding to the problem of space junk, there are also those who've expressed concerns that Starlink and other constellations could have a negative impact on astronomy. In response, SpaceX recently announced that it will be instituting changes in how satellites are launched, how they orbit the Earth, and even how they reflect, in order to minimize the impact they have on astronomy. Aside from Starlink's potential to provide the globe with broadband internet, they are also looking at installing receivers in major airline companies and other aircraft to provide consistent signal anywhere in the world.
Hi, my name is Tyler Kennedy, and welcome to the Jetpack. The idea for a personalized flight system, the Jetpack, was kind of started after World War II. So a lot of corporations saw kind of a need for, different military technologies. Obviously, the jet engine had just come out, so corporations ended up pouring a lot of resources into some new experimental technology. The jetpack was one of them. So the war kind of sparked the idea of this personal flight. And by the late 1950s, Bell Aerosystems began making it a reality. So on the right here, we have the SRLD, the Small Rocket Lift Device. This is the first ever jetpack. It was kind of designed and prototyped in the late 1950s. And by 1962, Wendell F. Moore patented this device. It could only fly for 20 seconds, but it could do, in that 20 seconds, it could do pretty much everything. It could go as high as you wanted. You could rotate left, right, up, down. But, you did have to find a place to land within 20 seconds. So here we have the functionality, the actual science behind the SRLD. It worked by sending a mix of pressurized hydrogen peroxide and compressed nitrogen through a decomposition catalyst. And what that does is it just breaks down the gas mixture into steam and oxygen. This steam and oxygen then entered the pipes, which are shown on that picture on the right there. And the pipes basically allow the gas to contract and expand very quickly, very rapidly. And this contraption, which contracted and expanded the gas, because the gas was changing density so quickly, it actually accelerated the gas to supersonic speed, which then created reactive thrust. So because the gas was moving so fast, it basically boosted the jetpack in the air and throwing the person who's wearing the jetpack in the air also. Here we have the SRLD make its public debut. This was the original Bell. This was his rocket belt, and it actually was in the opening ceremony of the 1984 Olympics. So check out this YouTube video. Personalized rocket technology has actually drastically improved since the 1960s. Flights now can last up to 8 minutes and reach maximum speeds of 40 miles an hour. that's for this particular rocket jet combo you see on this picture here. There are other jetpacks that can last longer and go slower, and lots of different designs. But the one that you see here, it can last up to 8 minutes and reach 40 miles an hour. That's actually a picture of a jetpack racing league. So this billionaire from the UK invented this jet technology, and he puts on shows and creates this race setup where these three highly skilled, trained flight rocket people fly around this buoy and race this course, which is pretty cool. So even though today it's not realistically feasible to use jetpacks as a mode of transportation, the vision of personalized flight is one that will definitely be improved upon, innovated. I think a lot of people are working to make this a reality. So even if it's not really feasible in the next 20 years, maybe by the time we're 60, we'll see jetpacks be kind of a bigger part of society. I think one of the reasons why jetpacks are so popular, one of the reasons why they will leave a legacy, is because they seem to kind of speak to the Rocketeer in all of us. We all want to be an astronaut. It calls on everyone's desire to fly. That's like the one superpower that everyone wants. I think jetpacks will really leave a legacy.